Good afternoon, everyone, and thank you for joining us for today's webinar. Today's webinar is the 11th webinar in the Forensic Technology Center of Excellence webinar series, Opioid Crisis, a Public Health Enemy. Rates of opioid use and misuse have reached epidemic proportions and are impacting many aspects of both criminal justice and forensic science programs. Opioid addiction is the driving force behind this increase in use, with nearly 3 million Americans reporting a substance use disorder to prescription painkillers or heroin in 2015, fueling a steady increase in fatalities to an estimated 91 U.S. deaths daily. These rates are not slowing. Rather, they are doubling, quadrupling, or undergoing even more alarming increases in some areas. Law enforcement, medical professionals, laboratories, and legal agencies are battling with unmanageable caseloads, economic shortfalls, and challenges for safety, analytical preparedness, and basic education and training. Reliable surveillance and intelligence are needed more than they have ever been, confronted with the fast-paced emerging drug life cycles. The legislative quagmire is just as burdensome, as policy change cannot happen without the data to support change. This webinar series will bring a multifaceted perspective to how diverse criminal justice disciplines are addressing these challenges, sharing their knowledge, and advancing science, technology, and law. Dealing with the impacts of the opioid crisis to the criminal justice system requires better reporting, surveillance, research, technology, and policy than are currently in use. The need to understand the epidemic and its effects goes beyond knowing your own profession. It takes a global perspective to fully act and make a difference. My name is Josh Vickers, and I will be the Forensic Technology Center of Excellence host for today's webinar. Today's webinar is entitled The North Carolina Statewide Medical Examiner System Laboratory Approach. We do have two wonderful presenters today from the state of North Carolina's Office of the Chief Medical Examiner. Our first presenter will be Dr. Ruth Winokur. She is currently the Chief Toxicologist for the state of North Carolina's Office of the Chief Medical Examiner in Raleigh, North Carolina. Under her direction since 1999, the laboratory is responsible for analytical testing, records maintenance, and review of analytical testing for greater than 11,000 medical examiner cases per year. Dr. Winokur has published articles, book chapters, and abstracts related to forensic toxicology, whose topics include analytical methodology, reviews of therapeutic and abused drugs, the toxicology of metals, and the measurement of therapeutic and abused drugs and alternative matrices. Additionally, she holds the academic position of Assistant Clinical Professor at the University of North Carolina School of Medicine, Department of Pathology and Laboratory Medicine. Our second presenter today is Dr. Justin Brower. He is currently a forensic toxicologist at the North Carolina Office of the Chief Medical Examiner as well, and a clinical assistant professor in the Department of Pathology and Laboratory Medicine at the University of North Carolina School of Medicine. He earned his PhD in organic chemistry at the University of Nevada and followed with a postdoctoral appointment at the University of California, Irvine, with a fellowship from the Cancer Research Institute. In a career change, he joined the North Carolina Office of the Chief Medical Examiner, where in addition to his normal duties of case review, he develops LC-MS-MS assays for routine and non-routine quantitative analysis, as well as targeted Orbitrap LC-MS-MS screening assays. Our quick disclaimer: the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenter and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. Now, without further ado, I would like to go ahead and hand the microphone over to Dr. Winokur and Dr. Brower for today's presentation.
Hello, everybody. Thank you for joining us today, and I also want to thank RTI for asking us to give a presentation in their series. At first, I thought, what does our lab have to offer this series? Because you have had other presentations about approaches, but I got to thinking about it, and I know that previously most of the presentations were about high-resolution instrumentation, and I wanted to show how a lab that has kind of a mix of instrumentation might approach this problem. And so I asked Dr. Brower if he would be happy to lend his technical expertise to the presentation, and so here we are today. So I'm going to talk about the OCME first, about the program overall and some of the statistics and what we're seeing. And then Dr. Brower will talk to you more about the technical program, and then we'll wrap it up with some epidemiology data from North Carolina, including why our data might be unique. So the OCME background, the Office of the Chief Medical Examiner investigates all sudden unexpected deaths in North Carolina, including all suspected drug-related deaths. The OCME collects data from autopsy reports, death certificates, investigation reports, and toxicology reports on all deaths investigated by the Medical Examiner System of North Carolina. The laboratory is the central laboratory for the Medical Examiner System. All cases come to our laboratory in Raleigh for analyses. And we're going to get to about 12,000 cases this year, and so every year, the last few years, has been a record for us. Also, in addition to an increase in the total number of cases that we've seen every year, the percent of accidental deaths that are attributed to poisonings has also gone up. So you can see in 2010, 23% of all accidental deaths were poisonings, but in 2016, that was 35% of all accidental deaths were poisonings. Accidental opioid deaths has also gone up dramatically. So back in 1999, when I took over as chief, we had about 2 opioid deaths a week in North Carolina, and last year in 2016, it's almost 4 a day. And the drugs have changed as well. These are the top 5 drugs causing death, going back all the way to 2000. As you can see, cocaine is a top visitor to this top 5 in all the years presented here. But heroin has been in and out of the top 5 over the time, and methadone has completely disappeared during this time frame. And so you can see heroin, it's in and out of the top 5, except in the last few years. And fentanyl, that's circled in red, is primarily or all pharmaceutical fentanyl in those years. But now fentanyl circled in green, this is all, or most of it, is illicitly manufactured fentanyl. And you can see in 2016 that fentanyl analogs as a group also entered into the top 5 drugs in poisoning deaths in 2016. So, as everybody knows, we've had a rise in fentanyl and heroin-related deaths. That's a 35% increase from 2015 to 2016. And 32% of heroin-related deaths also involved fentanyl in 2016. So the rate per 100,000 in North Carolina has gone up again dramatically in this time frame, over 1,000%. Also, you can see that in addition to opioid overdoses, in 2010, 2011, 2012, 2013, this is all pharmaceutical fentanyl, such as Duragesic and other forms of pharmaceutical fentanyl. But as the illicit fentanyl begins to get out, there you can see the percent of opioid overdoses that are positive for heroin, fentanyl, and or fentanyl analog has gone up dramatically. So the toxicology laboratory is accredited by the American Board of Forensic Toxicology. Most of our testing is performed in-house. Because of the dramatic increase in the number of cases that we have experienced in 2016 and 2017, we have used a reference laboratory for surge purposes and also to help with vacancies in the laboratory. And we're very lucky to have those kinds of resources so that we can keep our turnaround times to a reasonable level. But when we do a case in-house, we're testing for 600 plus compounds because we're using a combination of targeted and untargeted testing. And the testing is based on case history and pathologist requests. Like I mentioned before, the laboratory serves all 100 counties of North Carolina, and a certified toxicology report is issued to the pathologist. Case documents, including toxicology report, are sent to other requesters after all case procedures are complete. The effect on the laboratory has also been dramatic. So in 1999, where we had 100 total opioid overdoses for that year, we did 668 complete drug testing cases. So we tested 668 for what we call our complete testing. And we're on pace to do 3,600 cases in 2017. So like I said, the effect on the laboratory has been quite dramatic. As you can see here by this table, in the first quarter of 2016, we did just under 11. We did just over 1,000 what we call the LXQ screening tests, and 555 were positive for any opioid, and that generated 468 opioid tests and 312 fentanyl tests, but only 85 analog tests. In 2017, in the first quarter, we had almost 1,200 of those screens done and 383 analog tests, so a 350% increase in the number of analog confirmations and a 59% in the number of confirmations needed from the screening test. So again, a dramatic increase because these cases are not just positive for one opioid, they're positive for several. So the laboratory has seen not just opioids, but pretty much every single new or novel psychoactive substance class that's out there. And this basically shows you how many different types of new or novel psychoactive substances detected by the lab in each individual year. And other is things like methoxy-PCP or methoxetamine or the NBOM compounds, hallucinogens, whatnot. The stimulants are primarily what everybody calls bath salts or caffeinones and piperazines. And then, as you can see, the opioids have gone up dramatically during this time period. So, getting back to opioids. So the challenge to any post-mortem forensic toxicology laboratory is, that unknown unknown. How do you know that you have found everything you are looking for, right? So, this is a good example of part of our approach, and Dr. Brower is going to take over right after this, actually, and talk about how we've developed our approach since this time. So, in 2014 was when we first saw the acetylfentanyl, and that was our first and only analog for a long time. But in December of 2015, we have a very young woman who was found dead in her apartment. And everything was negative except for 4-ANPP. And so we knew we had a fentanyl because of the presence of the 4-ANPP, but we didn't know which one. It took us a while to obtain the powder from the death scene and analyze it. And we found a large peak, and it didn't give us a database match. But what we did was we looked out, we went to Google, I guess, and said what fentanyl analogs are out there. And we got a list, basically. And we looked for ones that there was not a library available in, say, Cayman or Swig drug, right? And then we worked it out. We got out our Silverstein manual and book, and we identified some of them that it might possibly be, and we worked it out. You know, does this fragment fit with the proposed molecular structure of this drug? But it wasn't until March of 2016 that furanol fentanyl was available, and then of course you have to go through your method development and validation. We finally issued a toxicology report in 2016. So after that time, we realized that, you know, this is kind of a haphazard approach, and we needed, you know, a better approach. But, you know, this is a good lesson in knowing that if you have 4-ANPP, then you know you've got some kind of fentanyl going on, because, you know, 4-ANPP is the core structure of that. Yeah, thanks. There it is. So that's the backbone of fentanyl, and that's furanol fentanyl. So you know that you've got a fentanyl when you have that, when you detect it. It turns out that the concentration of the furanol fentanyl in this case was so low that it wasn't detectable by our organic basic screen. But we were able to eventually quantitate it using a LCMS method. So I will leave this now, and I believe we have a poll, right? Mm-hmm. So if you'll just tell what kind of organization you're with. Okay, so it looks like most of us are forensic toxicologists here. So that'll be good. We'll all be into chemistry, because the next section's going to be on the chemistry.
Hi, this is Justin. Thanks for joining us today. I get to talk about all the geeky chemistry, mass spec stuff. And as Dr. Winokur alluded to, there's a lot of different techniques that are available to a modern post-mortem lab. And so we have, you know, our toxicology cat, nicknamed VOD-cat, and there's more than one way to skin it. So most laboratory processes are dictated by several things, one of which is your lab, not only the size of your lab, both in personnel and the number of cases that you do, but also what type of lab you are, whether it's a crime lab, a drug lab, or a postmortem lab like ours. We strictly do postmortem, but there are a lot of labs out there that will do 1, 2, 3, or some sort of combination of them. And your goals are also important too. Is it important to just find a cause of death and move on, or has someone established goals where you have to be very comprehensive and, you know, find every last drug available for, you know, epidemiology type work? Or there's lots of shades in between as well. But also, you know, your resources. A lot of people, when they hear resources, they think about money, and of course money's, you know, important to keep, you know, the lights on in your lab. But your most precious resources really are your personnel and your time. And so you want to maximize those as much as you possibly can. And obviously, new technologies or techniques or assays can really help preserve your personnel and time. Most labs have some sort of drug problem. You probably wouldn't be here if your area didn't have an opioid problem. And, you know, we certainly have our fair share, as Dr. Winokur has shown. We don't have a lot of Renaissance fairs in North Carolina that I know of, but I'm waiting. So we're constantly facing new drugs, and we're always looking for, you know, appropriate and new screening techniques to detect these new drugs. Common techniques are immunoassays. There's also non-targeted assays that Dr. Winokur talked about, such as like a full scan GCMS assay or an LCMS assay, but also targeted either by LC or currently Orbitraps or TOS, QTOS are common tools for targeted screening assays. But you can also outsource them as well. Those are for the labs that have a lot of money. For immunoassays, some of the benefits of it are that they're class-specific. So you can have one kit that might capture many different drugs within that class, such as an opiate or an opioid assay. And they're typically fairly quick and easy to run, unless you're in a post-mortem lab where it might require more workup, more sample preparation. Some of the cons, there could be unknown or no cross-reactivities. You just really never know what the cross-reactivity of a brand new compounds, whatever the new Fentolog, coming our way is, it may be it doesn't cross-react well in the fentanyl or Fentolog kit that you're using. So you have the possibility of having false positives. False positives, no one likes to hear that word, but if you're doing confirmations, no harm is done. It's not going to be reported out. But the false negatives, the things that you're not detecting in your screen, you'll never know. They're just pretty much lost forever. But also, you have to use a lot of kits nowadays. It's no longer you just content with doing benzos and cocaine and some heroin. There are so many other drugs out there and so many kits available. It can be really expensive, and all those $2 or $3 kits per test per case add up pretty fast. And that was one of the reasons why we stopped using an immunoassay. It worked to a degree for us, but we had outgrown it, and it was just costing us a lot of money. And so then we moved to a targeted assay on an old thermal ion trap, LCMS. With immunoassays, you really just don't know, again, what you're missing. The next Fentolog, say like Adamantal, fentanyl, it's not out there yet, probably won't be, but does it cross-react? I have no idea, no one really does. For non-targeted assays, the pros are that they're often cheap with existing equipment. A lot of labs have a GCMS lying around. I mean, the Agilents typically never break down, and so they'll stay in the lab forever. And they have the ability to detect a wide variety of compounds. Dr. Winokur mentioned that we screen for about 600 plus different compounds in our GCMS assay. So it has great utility in a wide scope of compounds that it can detect. On the downside, though, is sensitivity. GCMS just isn't quite as sensitive as LCMS technology. And it can also be pretty data intensive. So it could require a lot of work on the analyst's part and the reviewer's part to process and go through all that data looking for all of these drugs. But I guess that's kind of the point of having this talk. You also don't know what you're missing. If there's some new opioid or fentanyl out there, are you really sure that you're seeing it within the limits of detection that you need? Does it extract well? Is it surviving the GC? You don't really know. So your limitations in general are kind of unknown. With the targeted assays, and speaking specifically towards the LCMS side of things, it has good selectivity. Sensitivity is great. If you throw a couple calibrators in there, you can get some semi-quantitative idea of what concentrations you're looking at. But you really do have to know exactly what you're looking for. It is a targeted assay. So if you're not telling the method what to look for, it's probably not going to find it. And it can also be an expensive area to enter. Instruments aren't free nowadays. But on the plus side, your limitations are known. Again, you're only looking exactly for what you tell the instrument method to look for. So I guess it's a pro and a con. And as far as outsourcing, it doesn't really get much easier than this. You just need a throw a specimen in a box and ship it off to your nearest reference lab or your favorite reference lab. But the cons are that it can be really expensive. Of course, depending upon the number of cases you send out. If you have, a couple cases a year or a month, it's not that bad, and it might be beneficial and more cost-effective to outsource your work rather than funding a lab, equipment, overhead, and so forth. But you're also limited by their assays. So when new drugs are making the rounds, it takes time for a reference lab to develop the assay, know that it's out there, validate it, and then offer it to the public. So there could be a 6-month or a year time lag before they can offer it. And so it's really not optimized for your casework and what you're seeing in your regional area right now. So there's really pros and cons to everything. But what we've done is we've taken a two-pronged approach. We use a non-targeted GCMS assay, again, covering most pharmaceuticals and many illicit drugs, coupled with a targeted LC-MS assay, where we've instructed it to look for 70-plus, illicits and drugs of abuse, including 34 fentanylogs and 7 designer opioids, and a bunch of, new designer benzos as well. And this is always an evolving method where it seems like we're adding a new fentanyl every day, practically, as we're made aware of them. And so these are things that, kind of like the word on the street or drug forms, mention some new fentanyl. We can target it specifically and then wait for a reference standard to be made. But we kind of have a head start in a lot of cases. And it works for us. And that's really the key, is to find out what works well for your lab and to run with it. So for our non-targeted GCMS, and this is kind of what gave Dr. Winokur the idea of doing this type of presentation, is not all labs have access to an Orbitrap or a TOF to do cutting edge toxicology work. You can really get a lot of information from that old Agilent that's sitting in your lab. Hopefully you're using it because they're great instruments. But you can get a lot of information out of it. The furanylfentanyl example that Dr. Winokur mentioned, that was exclusively on, it was probably this instrument right there, GC13. It's a liquid-liquid extraction using 2 milliliters of typically a central blood specimen. But really, any type of specimen we can throw in a test tube, we've probably extracted it. So liver, brain, spleen fluids, we've done bone before. If it fits in a test tube, we'll extract it. The key for the opioids, and specifically fentanyls, which I'll focus on, is really in the fragmentation. And to understand and be able to recognize new fentanyls or fentanylogs, you really need to understand how fentanyl fragments. And you've probably seen this spectra before. It's got a common 245, 189, 146 ions. But not a lot of people spend the time to think about where these are actually coming from. And these things fragment very predictably. You're really just taking a large molecule and smashing it up, into smaller pieces, smaller fragments. So we'll start with the 245. The 245 is coming from the cleavage of this benzyl group from the phenethylamine moiety. And this is common with practically all of the fentanylogs that we see. The 189 is coming from the cleavage of the propionyl group of the propionamide moiety. And then the 146 is coming from this, let me grab this arrow, coming from this part here. It's really not quite that simple. It's actually forming a, oops, I need a pen. There we go. It's actually forming a cyclobutyl group here, and then it's got a positive charge carbocation here. I told you I was kind of a geek, but that's common again in most of the pentalogs that we see. I should probably get rid of this. So when we look at a pentalog, such as butyrylfentanyl, the key is to, at first, kind of recognize that, hey, it's got this same type of fentanyl fragmentation pattern, maybe not the exact same ions, but you can kind of recognize that it's very similar, and that's key. And then compare it back to fentanyl. So compared to fentanyl, where we see the 245, 189, 146, we're seeing a 259, a plus 14, which most people will recognize as a CH2 group, a methylene group. Well, now you just need to know, well, where's that coming from? Again, we have the cleavage of the benzyl group, and we're seeing the 259. So all of this part here is the 259, and we've got that plus 14. So we know there's a methylene, a CH2, somewhere on here. And then the cleavage of the 189. So we've cleaved off this amide group here. So we know that since this is conserved, the same as with fentanyl, we know that we have a plus 14 somewhere on this amide side chain, and that would give us butyrylfentanyl. Now, we may not know if it's butyryl or isobutyrylfentanyl. That would have to be addressed in confirmation, but you've got a really good idea of what the basic structure is just from looking at a simple GCMS spectra. And you have the 146. Can't forget that cyclobutyl moiety there. Moving on to something a little bit more complex, such as fluorobutyryl, or what we see here is fluoroisobutyrylfentanyl. We see a ton of that here. I'm sure you guys do too. Again, recognize this type of pattern, and here it's not the same ions, but they've got the same sort of spacing. It kind of looks very similar. And this is where we've trained our analysts to kind of recognize, and they can bring the spectra up to me and say, hey, this isn't fentanyl. It's not coming up in any of our libraries. We typically use the Cayman drug library, available for free from Cayman, and also a SWIG drug library. And they'll say, hey, it's not coming up for anything, but it looks like a fentanyl. What do you think it is? And then we can sit down and really just work through this exercise. So here we're seeing a plus 18 and a plus 32. Again, looking to see, knowing how this fragments. We've got this plus 32, which is pretty odd. But then when we look at the 207, we're seeing a plus 18. If you subtract the 18 from the 32, you're left with 14. I'm not a mathematician, but I think that's right. You're left with a 14. So you know that when you subtract the two fragments, just doing some basic algebra, you've got a methylene group here on this side chain. And then, again, looking at the 164, we've got a plus 18. You can check your Silverstein book or a periodic table or something like that, and you know that if you replace a hydrogen with a fluorine, that would give rise to a plus 18. Now, you don't necessarily know where that fluorine is. It could be anywhere on here. It won't tell you ortho, meta, para. Perhaps, if you're looking in the weeds down here, you might get some clue. I don't think so. But at least you have an idea of what the general structure is. And again, it won't tell you butyryl or isobutyryl. But you've got a really good guess as to what it is. So let's look at this example, 3-methylfentanyl. Again, you've got a familiar type of pattern here. It looks fentanyl-like. Fragmenting it, plus 14, that makes sense. And before we had a plus 14 over here when it was homologated to the butyryl. Oops. And again, looking at the 203, we've got a plus 14. So that's telling us that there's a methylene group somewhere in this area. And the same thing when we look at the 160. We've got a methyl group somewhere. It's not telling us if it's in the 2 or the 3 position or if it's on this benzene ring, but it's giving you a good clue as to what it might be. And also some of this finer detail down here could help you out, but I don't want to get into the nitty-gritty stuff. Just want to focus on these 3 ions that will really just tell you a lot of information. So best practices, I think, for a GC mass spec non-targeted assay is that extracting the ions is probably not as helpful as you would think it is. You know, we extract for 6 common ions when we're reviewing our base loads. And fentanyl is one of them. We're looking for that 245. But as you saw, you know, just about any type of change on that fentanyl, every type of fentanyl log that you see practically is going to have something larger than that 245. So it's really not going to help you out. The best thing to do is really just what I call click on the junk. You know, you're looking at fentanyls, you're looking at low doses, low concentrations in blood or tissue, mostly low in blood. And you just got to click around and look at the spectra and recognize that, hey, it looks like something. Compare it to fentanyl, look to see what fragments are different, what's conserved. And then if you figure something out or you find something new and exciting, you know, share it with your lab and teach them. And everyone in your lab will be better off for it. So to give a real-life example, this was one of our cases. I believe this is urine. I didn't double-check, but I think it is. That's a noisy chromatogram, a noisy tick. But this little peak here that I have highlighted with the red arrow, and now I have a green arrow on there, so it's kind of Christmassy, that gave rise to the spectra. Again, we see this 146, 189, 243. That looks and sounds pretty similar to fentanyl, the 146, 189, 245. So 245, 243, that's kind of weird. But it looks like fentanyl. Only we're seeing a difference of 2. We're seeing 2 less. And so the question is, you know, what gives a -2? I can't hear what you're saying right now. I'm hoping somebody, well, if you said helium, I'd be kind of proud that you know it could be a possibility, but it's really not going to happen at all. Helium doesn't covalently bind that way or bond that way. But instead, what we figured out is that it's acryl fentanyl, which we've seen several times in this lab, and I know other labs across the nation have seen as well. So this was one of our first instances of acryl fentanyl, and again, losing 2 hydrogens here to give the 243 instead of the 245. So, excuse me. So moving ahead to the targeted screening, we have a procedure that's much simpler than a liquid-liquid extraction. It's just a protein precipitation from 0.5 mils of specimen, typically blood. And then reconstituted in a phosphate buffer, and we use a thermo-Q exactive focus, LC, MS, MS. It's a parallel reaction monitoring instrument method with an inclusion list. And it's really pretty simple. All you're really doing is adding the molecular formula and a retention time window for it to scan. So it is using a version of high-res mass spec to do its screening. But what about isobaric or isomeric compounds? The first thing, you would hope that they separate chromatographically. That's always important. That would be great, but it doesn't always happen. But with GCMS, you can look at the spectra and then optimize your processing method accordingly. So I'll use the example here of fentanyl. So fentanyl 4-methyl-phenethylacetylfentanyl and alpha-methyl-acetylfentanyl all have the same molecular weight, same molecular formula. And how would you separate these? How would you distinguish one from the other? So, I mean, it's pretty well established that fragmentation by GC and LC are different. And for fentanyl, what you see is a common 105-188 fragment. The 105 comes from the cleavage of the phenethyl group. LCMS loves to fragment carbon-nitrogen bonds. The 188 is coming from cleavage here, again, a carbon-nitrogen bond. So this is the genesis of the stereotypical 188-105 fragmentation pattern for fentanyl. When you move on to the 4-methyl-phenethylacetylfentanyl, which I don't believe we've had a case of, but you never know, we look at the cleavage of that phenethylamine group, and we see compared to fentanyl a plus 14. So what that's telling us is that somewhere on here there's a methyl group. Again, not telling us if it's ortho, meta, or para position, but somewhere on this aromatic ring. And again, that's shown again with this 202. So if you're just looking at this 202 fragment here, you know that there's a methyl group somewhere on this fragment. And then with the 119, it's kind of narrowing it down even further to this area. The alpha methyl here, I'm kind of going backwards. I'm showing you that the 202 fragment, again, methyl group somewhere here. But when you have substituents on the alpha position, such as alpha methyl, you get a 91 instead. So it's really cleaving off a benzyl group instead. So you see a 91 202, and we're just trained now so that if we see a 91 and like a 202 or 91 something else, we know that is probably an alpha substituted fentanyl analog. So you've got a lot of ions to choose from, but you need to choose wisely. And so when you look at kind of the summary of the fentanyl and the other two fentanyl analogs I don't really want to repeat their names of, we have three that are very different, a 105, a 119, and 91. So you can optimize your processing method for each one of those ions to distinguish between them. And then you also have another secondary set of ions that would help distinguish between fentanyl and then those other two analogs as well if you need to. So taking what we just learned, what would you predict for para-methyl-acetylfentanyl? So we'd go through and we'd cleave off that phenethylamine to give the 105, and then, we got a 188. This looks just like fentanyl. So what are you going to do besides praying for some sort of chromatographic resolution and separation? Well, you can always go back to the GC and look to see what you'd observe there in the spectra. And here, compared to fentanyl, where you see the 245 and the 146, for the para-methyl-acetylfentanyl, you see the 245, but you're seeing a 160. So this is really just telling you that you've got a methyl group somewhere on this fragment here. So really where the Orbitrap LCMS, great brand new technology, we love it, but it wouldn't be able to distinguish between the fentanyl and the para-methyl-acetylfentanyl the way it's set up now. And so really that old GCMS that we use every day in our lab is still very, very useful, and really playing off the two techniques can give us a whole lot of information and help us solve a lot of problems in our cases. So the take-home nuggets for you today, for the rest of my part, and then hand this back over to Dr. Winokur, is really to choose the techniques that are best suited for your lab, ones that fit your needs and your goals. And you really don't need the latest and greatest instrumentation. The best tool for the job is you and what you can figure out. I mean, you're all probably great problem solvers. Most toxicologists are. It's pretty much what we do for a living. So work through those problems, learn, teach, and share. And it's something I do when I encounter, just even online, if there's a new fentanyl that I'm made aware of, try to predict how it's going to break apart in both the GC and the LC. I have blank worksheets with the fentanyl backbone, and I'll draw the structures and break down where it's going to fragment. And so it's incredibly useful. Make sure you share that information with your lab, but also keep up with the current trends. And again, see what's out there. So, talk to people locally if you have a local crime lab that can help you out and tell you what they're finding on the streets, and your colleagues in neighboring states and internationally, as a lot of these drugs tend to start over in Europe first and kind of, make their way over here. So I believe that's the end of my portion. Our email addresses will be given out by Josh, and I think they're on the very, very, very last slide. And so if you have any questions, again, you can type those questions in now, or if you would rather, you can always call or email. I'm always willing to help other labs and other people with their problems. And I believe we have another poll question.
I think we're going to answer some of the questions first, are we? I can't hear Josh, but...
So,
we'll
what is your lab's primary...
And to answer the questions.
Okay, because those are good questions.
Yeah.
Yeah. Dr. Craner has a good question. I like that one. All right. So the poll question is...
That's a good question.
Yeah. The answer, Dr. Craner, if you're listening, is yes.
Yeah.
So what is your lab's primary screening technique? It looks like a lot of people use immunoassay. Targeted is coming in second, rounding up third. This is like the Kentucky Derby. This is fun. A lot of non-targeted as well. 4% are taking the very, very easy way out with the outsourcing. Go outsourcing. I'm inherently lazy, I think, so I think it's a good plan. And other. I'm curious about what the others might be. So maybe if you can put those in the comments, I'd be curious to see what the other is. Probably a combination of several techniques. Hopefully it's not TLC. So I'll hand this over to Dr. Winokur, and she'll bring this home.
All right, thanks, Justin. So, getting back to, the opioids epidemic, I know we focus a lot on fentanylogs, and I can tell you that we've also seen the U compounds on the GCMS just using regular basic screen. That's not all the opioids out there. It's not all the psychoactive substances out there either. And if you don't know what you're looking for, you might miss something. I mentioned in the beginning when we talked about that first furanol fentanyl case that we were able to figure that one out. The concentration was so low that it wasn't detectable by our organic basic screen, but we did find the 4-AMPP. And so, again, that led us to the information is that, we know we have a fentanyl, and so then you're able to get physical evidence and then figure out from there something with a high concentration of the drug, okay? But you still might not know what you're missing, and that's, we have a recent case, a 24-year-old research chemical enthusiast who only had a little bit of alcohol and a little bit of a tizolam present in the case, and so it certainly was not enough to have caused the death. And, you really shouldn't be dead at 24 years old unless you have some, really horrible disease. And this person didn't. And so, again, going back to finding physical evidence at the scene, then you can take a look at those. And this case, it turned out to be tianeptine, which has some opioid or some activity at the mu-opioid receptor, and also phenibut. And both of these compounds would neither be detected by any of our, at that time, what was our current detection scheme. And so, you know, we don't just call it done, okay? We finished the toxicology on this case. We didn't have a cause of death. We knew it should have been a drug overdose, so what do you do next? And so you look. Phenaptine has a carboxylic acid group on it. There are some metabolites that do show up in the organic basic screen. Phenibut looks just like gabapentin pregabalin, so it's not going to come out under any sort of liquid-liquid type extraction. And so we're just not going to see it. And so we've consequently gone back and added these to our targeted screen. And you know, now we can find them in cases, and we've found them in several cases. So just, you know, keeping your eyes open. So I want to get back to OCME, and one of the things that when we start talking about counting, you know, the different fentanyl analogs and you know what is in these cases that, you know, we lump all under the opioid death, I think it's important to link a death to a particular drug. And ICD-10 codes, you know, they aren't that useful, basically. So death certificate data can, you know, cause you a problem. And we do have some medical examiners out there that will just put simply multi-drug toxicity on a death, and so that can also cause you a problem. So while the CDC has come out with guidelines that ask, you know, that instead of you know, multi-drug toxicity or polypharmacy or whatever might get put on, that you actually list the drugs. It really doesn't tell you, that death certificate data doesn't tell you, you know, what role that particular drug played in the death. And so, again, going back to death certificate data, so going back to acetylfentanyl, all right? If you look at ICD-10 codes, this death, okay, would have gotten classified as an X42, maybe a F11.1, or a T40.4, which is other synthetic narcotics. So if you were counting acetylfentanyl deaths, right, you wouldn't be able to differentiate this from any other fentanyl analog. So it fails to specifically say, and that can impact policy decisions, particularly scheduling of these individual compounds. But it's the OCME, the toxicology drug cause worksheet. So after the toxicology report is issued to the pathologist, a worksheet is also issued to the case. And every case in North Carolina is reviewed at the OCME or in the Mecklenburg office. And one of these worksheets will accompany the toxicology report. That allows the pathologist to attribute the drug to how it was related to the death. Okay, so instead of a drug, you know, death certificate that might say cocaine, that's not a good example, or that might say, you know, heroin, alprazolam, and, you know, amitriptyline toxicity, okay, the pathologist gets to say what role each individual drug played in that death, whether the drug was present at a concentration that could independently have caused the death, regardless of other substances that are present, or that drug played an additive role, right, and was present at a concentration that was only in combination with other drugs could have caused the death, or the drug acted in a way indirectly, so a behavioral effect such as ethanol and motor vehicle fatalities. So, you know, that brings me to the end, and that's good because we only have 5 minutes for questions. But if someone wants some of this OCME data, like, you know, what deaths were caused by which particular drug, You know, the OSME data can be requested through our website. And then again, Justin's and my email addresses are right there as well if you have any questions. So we'll start at the top here. So what are the most frequently delivery methods of the analog syringe powder? What are you seeing? We're seeing syringes, we're seeing snorting, pretty much that's it. I don't think I've seen any smoking, although we do have some that are being sold as cocaine, so you know, you just never know. Then did we completely omit fentanyl ELISA from your screening panel, being that there's still some cross-reactivity with the fentanyl analogs? Well, the cross-reactivity is all over the place, but I have to tell you, we eliminated the ELISAs back in 2010 when it was very difficult to get a fentanyl kit. There was a problem with the antibodies, et cetera, and so it just made sense to us, given that the cross-reactivities really were all over the place, particularly with the benzos and some of the other opioids, and we were looking at having to add a buprenorphine ELISA to our, you know, and the benzo one didn't even pick up clonazepam all that well, so we just went to a targeted screen. And as it turns out, I think with the exception of carfentanil, we've seen all those analogs in the organic bases screened first. And we also, another thing that we do is we keep a list of cases that should be drug overdoses where we're coming up negative, and then we'll go back and reanalyze them at a later date when we have added more analogs and whatnot to the targeted screen. So Dr. Craner, good to see you or hear from you or whatever here.
We can't hear you.
Yeah. Can your lab distinguish between cyclopropyl from fentanyl? The answer is yes, not on the Orbitrap.
Correct. So they, again, isomers of each other. They do co-elute. So we actually did obtain 2 reference standards for each. They co-elute, same spectra, identical. But after we do our confirmation by LC-MS triple quad, we then run it through another assay that has a much shallower LC gradient, and by that, I mean, it's nearly isocratic. We're able to separate the crotonil from the cyclopropyl fentanyl, and we have not seen any crotonil fentanyl in all of our cases, and we've, at this time, I bet more than 100 cases or so, and never seen any crotonil.
Yeah, we're over 150 cyclopropyl fentanyls at this point. Justin should teach at Soft in the Academy. Yes, he should. I agree.
I do have soft workshops, and so does Dr. Winokur.
Yeah, we're both teaching at the soft workshop in Boca Raton. Let's see. What is your case backlog? Well, it's not too bad. The most of our backlog is actually in compounds that we haven't developed and validated method for, either because we haven't gotten a reference standard yet, or we just haven't had time to develop and validate the method. The U compounds are the ones we're working on now. So we have 3 U compounds, 47700, 49900, and
51754.
Right
That's
now
popped up
that
recently quite a bit.
Got.
But I'm going on vacation as soon as we hang up, and that's my job when I get back.
Yes. Does the presence of 4-AMPP strictly mean a fentanyl? No, it does not. It's the backbone to all those fentanyl analogs. So, Lorraine Edwards, our pathologists at North Carolina, part of the NC OCME. So we have the OCME, which is in Raleigh, okay, and then we have 9 regional autopsy centers around the state, right? And so that, and then we have medical examiners in every county, so that explains. So Jerry says, in addition to combinations of opioids, what are the other combination trends on the rise? So the other combination trends are designer benzos with the opioids. Methamphetamine has a huge increase in our state. And we used to have only less than 10, 15, 20 cases a year, and we're well over 100 for 2016. And also cocaine. Yes. Sorry. In your case presented earlier, was fentanyl identified as the cause of death? Yes, it was. It was the only drug present in a otherwise healthy individual. And is cyclopropyl fentanyl? Yes.
Cyclopentyl.
Oh, cyclopentyl. Yes.
Yes, it is.
Mm-hmm. Does your lab work out state? I mean, do we take reference cases? The answer is no. We only do cases that are part of the North Carolina Medical Examiner System.
To get back to Lindsay's question about the 4-ANPP being strictly from illicit fentanyl or fentanyl analogs, strictly or absolutely no, but it really is a key indicator that it's coming from illicitly manufactured fentanyl or a fentanyl. I believe it's purity in the synthesis of it, and I've gone back into our GCMS data pre-fentanyl days, like say old data from like 2012, and looked at high fentanyl concentration cases, and I haven't been able to find 4-ANPP as a metabolite. Now, maybe you would in like liver or urine, but in blood, no. And so when we see it now, we pretty much have 99.9% confidence that's probably coming from an illicit.
And we've seen it also in the physical evidence from the scene. So we'll get, a powder from a scene, and it'll have 4-MPP. It'll have, the last one we did have methoxyacetylfentanyl, and it also had some heroin in it. So it's actually present in what the person is ingesting. Okay?
I think that's all the questions. And we can't hear Josh.
No.
Sorry about that. I was on mute. So yes, we did finish off the questions for today. We're going to go ahead and move on to our closing. Before I go through our closing, is there any parting words that you and your office would like to leave for our audience today?
Oh, well, I think that when we approached those, we wanted to give people some idea that you don't necessarily have to have the fancy Orbitrap or TOF to do this work. And like I mentioned before, every time we've seen one of these compounds, with the exception of carfentanil, it's been detected first in that regular old liquid or GCMS organic base screen. So I thought it was important to get that out there.
Yeah.
And again, we're available for questions or whatever, so via email.
All right. Thank you both so much. We definitely appreciate your time and willingness to give our audience a great webinar today. Again, we would like to thank our subject matter experts for their presentation today, and we would also like to thank all of our attendees who joined us today. These webinars are definitely not possible without your attendance and your support. Down there in the bottom left-hand corner of your screen, you will see a PDF version of today's slide deck. So go ahead and click on the title of that file, and then you will see the download files button will highlight for you, and you can download that directly from the room before you leave today. So please make sure to get that. Also in the center of your screen, we would like everyone to take a few moments of your time and complete our customer satisfaction survey. So simply click on the word here, and it will bring up a new window for you. Your feedback about our webinars is vital information that we always use to make sure we provide you the best webinar experience and adjust any content and the way we disseminate that information out to you, our audience. So please take a few moments to complete that survey. We would definitely appreciate it. Again, we do want to thank everybody for attending today. We hope everyone found the webinar very useful and informative. Please make sure to check out our website. I just opened a new browser up for everyone on their computers to our Forensic Technology Center of Excellence website. So please go ahead and check out all of our course offerings, both our upcoming live events, part of this opioid series, as well as everything that we have archived and recorded. Again, thank you very much, Dr. Winokur and Dr. Brower, for your presentation, and we hope everyone has a great rest of your afternoon.